Okay, so this will be an introductory lecture, very basic one, so for many of you will be very boring, and there is nothing that you don't know, but okay. I know that not all of you have the same background, so for many people will be new. And the lecture will be quite complementary to what Peter just did, because he covered the open quantum system. Instead, I will discuss closed quantum systems. So what I will cover is the out of equilibrium dynamic, of isolated okay, and the goal of our lecture is to understand how relaxation and thermalization happens in many body quantum system. And this is complementary to what Dima will do next week, because he will describe ergodicity breaking in the same kind of system. Okay, so this is, let's say, I will present the standard, and Dima will present the exception, which are extremely interesting, obviously, as all exceptions are. The standard things are boring, and the exceptions are the interesting part, usually, okay? But I will anticipate some exception even here, so. Okay. Just to fix the idea, I will describe what is known as quantum quench. In which a system is prepared in a state psi naught. This is the initial state. And then is let evolve with an Hamiltonian H. A many-body Hamiltonian H. And psi naught is not an eigenstate of H. And this you write in formula saying that the projector of psi naught doesn't commute with the Hamiltonian. If it would be an eigenstate, they will commute, but they don't, and so it's not an eigenstate. The time evolution, as you know by basic quantum mechanics, is just given by e to the minus EHT applied to psi naught. Obviously, we have working unit where h bar is equal to 1. Okay, you learn in basic quantum mechanics how to solve this equation for one particle, for one body physics. Maybe you did something also for 2, 3 particles. This is relatively easy. But this very simple equation, as the constituents of your system increase, becomes more and more complicated. And actually, if you didn't realize yet, the reason why we are building quantum computer is exactly to use this equation in one form or another, okay? As the time passes, this starts entangling things, and things get very complicated. Okay, so what are the questions that we ask? Questions. So the first question is it possible that for large time, so t that goes to infinity, the system attain a stationary state second question. Can this stationary state be thermal? Obviously, these two questions, from your knowledge of quantum mechanics, are complete nonsense. Okay? You know very well that if you have, for example, one body, the state will evolve always, and will oscillate very likely, and will never attain a stationary state. If you start increasing the number of constituents, you expect there may be the period increase, but things will be always quasi-periodic, and there should be no stationary state. But okay, while you can find some way out for the first question, the second question seems even more crazy. Okay, we have a pure state psi naught. We let it evolve with unitary. The state at any time, this psi t, is a pure state. Okay, a thermal state is like a Gibbs ensemble, e to the minus h divided by t. This is mixed state, as you know. It has non-zero entropy, while that guy has zero entropy. There is something wrong going on. Still, this kind of question are not very modern question. There is a very famous paper of John von Neumann in 1929, where he asked exactly this question, and he tried to find the first answer to that. And the paper you can find on the archive is very instructive to read. It was not the ghost of von Neumann that posted it on the archive, but some eminent scientist realized that we were a bit reinventing the wheel, because von Neumann answered already some of the question, and actually he posed in a very proper way already in 1929. And okay, before exactly reinventing the wheel, let's go to study this, what von Neumann did. But the reason why from 1929 there was not much activity is because this question was really academic. But everything changed in the last 20 years, I would say, 15, 20 years, thanks to the development of cold atom and ion trap techniques, in which the dynamic is really almost unitary. The coupling to the environment is very small. And I want to mention one pioneering experiment. Now, it's a very old experiment. Nowadays, there are much better experiments. But I want to mention an old one of 2006, which is the quantum Newton cradle. This was done in the group of David Weiss at Penn State University. It is published on Nature. 440, page 900, year 2006. And okay, it was really a pioneering experiment for the time, and really show all ingredients that we need for ergodicity and for its breaking. And as I said, nowadays there are more precise experiments and much better understood setting. But okay, the idea of this experiment is very simple. Okay, what they did, they prepared a quantum gas at very low temperature in the middle of an harmonic trap. The plot is one-dimensional, but they did in 1, 2, and 3 dimensions. Okay? At some time, so this was in equilibrium, at some time t equal to 0, they shine a laser on this cloud in the proper direction, so that to open this, to give opposite momentum to this cloud, realizing two counter-propagating packets, okay, that start going in opposite direction. Okay. And then they don't do anything else, they just observe what happened. What happened is similar to what would happen in classical physics. This packet climbed the potential, arrived to the maximum value allowed by the energy conservation, like when you roll a ball up to the hill. Then arrive at the maximum, they go back, okay? But when they are arrive back in the middle of the trap, like if they were two ball, they interact, okay? So they pass through each other and they reclimb the potential. So this is free evolution, and then they go back. And they go back and forth like this, okay? And what they mention is what is known as momentum distribution function, but this is not really important, okay? The main conclusion that they draw from this experiment, so results, is that in 2 and 3 dimension, the system thermalizes after very few oscillation. And few, it means like 5 for 3D and 9 for 2D. It's a very small number. So they blank, then they blob, and thermalize mean that this momentum distribution function assume the Maxwell-Boltzmann distribution at temperature of momentum distribution function, okay? So this is the first result. And the second result is that in 1 dimension, the system relaxes very slowly. How much slowly depends on interaction that they can tune, and for the strongest interaction they had, it took for the smallest interaction they have, it takes longer, and it took like about 2,000 oscillations to get there. So we are really talking about several orders of magnitude of difference. But relax very slowly to a non-thermal distribution. To a really qualitative different distribution, just to let you understand what we are talking about. I sketch in 2 and 3D. You have a momentum distribution function that after some time is usual Gaussian, which is the Boltzmann function, Maxwell-Boltzmann distribution. Okay. Instead, in 1D, they get something that looks up like this, so completely non-Gaussian, and these peaks have to do with the initial momentum that you give to the cloud, saying that the system is keeping memory of the initial state. Okay? But, okay, you could say, nothing new under the sun. This is exactly what happened in classical system, okay? Because if a system is generic or ergodic, system do thermalize, to integrable system, or nearly integrable system, do not. That's exactly what we know in classical physics, and it's the, if you want, the chaos hypothesis. Still, we observe this experiment show this undoubtedly true, but we should fit these expectations in our understanding of quantum system. The problem that I stated at the beginning that, okay, a pure state cannot become mixed is still there, okay? There is an experiment, shows that we should wonder how this happens, so these two expectations are correct, but we should understand how, okay, and in which sense, because say just like this, they don't fit our understanding of quantum mechanics, our understanding and our formulation of quantum mechanics. Okay, the fundamental concept to understand this, and now is the reduced density matrix, that probably all of you already knows what it is, but okay, let's just recapitulate the thing. So we consider a many-body quantum system, which is in a state that is evolving according to this equation. Okay? And we have the density matrix is just rho of t, the projector on the time-independent state. And being a projector, it has zero entropy. Okay, now we imagine our system to live in some space. Okay, and we imagine to divide it in two parts, a smaller part, which is A, and a larger part that is B. And we construct the reduced density matrix by definition. It's just the trace over the degrees of freedom belonging to B of rho of T. Okay, here we are assuming implicitly that the Hilbert space factorizes HA tensor HB, which is true for most of the system you can have in mind. Actually, do you have any idea why when this is not the case? Hmm? No, spatially. I'm saying you make a division in space, okay, and the spatial bipartition induce a Hilbert space bipartition. Two? It's not completely clear, but probably you are right. Not but what I was thinking is many-body quantum systems. So here you have many degrees of freedom around, okay? Like many spins, many a lattice model of boson of fermion, these kind of things, okay? One situation where surely this bipartition is not automatic and things are more complicated is, for example, in gauge theories, okay? Since okay, you can imagine why. Okay, and this reduced density matrix is very important because all local observable within A can be written in terms of rho A of t, in the sense that the expectation value of an operator which is localized, so x1, xn all belong to A, is just equal to trace of rho A of t okay, and fortunately this is the case, because if it will not be the case, to calculate the expectation value of an operator, we should know what is happening in Alpha Centauri, and okay, we would prefer to limit our observation locally, okay? Yeah? Gauge theory, yes. The choice of gauge is not local, so when you choose, a bipartition will be non-gauge invariant, okay? Yeah, but was just a parenthesis to say, take care that we always use this correspondence, but in some cases this is not possible, okay? In 99% of what you do in your life, it's just goes smoothly, but okay, sometimes can happen. That is not the case. Okay, and now we start seeing the light, because while rho A of t is a pure state, rho t, sorry, rho A of t usually correspond to a mixed state with a non-zero entropy. An entropy which is nothing but the famous entanglement entropy. Okay, and the entanglement entropy, as maybe many of you know, is a measure of bipartite entanglement that there is between A and B. Okay, just for the, if there is someone in the room that has never seen the entanglement entropy, I want to make a very simple example. Imagine that you have a quantum state psi, which is constructed as the product of singlets, okay? Singlet states, so like between site I and J, okay? So imagine you have your lattice model, and you have some singlets going at very different distances, okay, something like that, and then you focus on a region A, okay, you see that all the singlets that are within A or within B don't contribute to the entanglement entropy, but if there are lines like this one that goes from here to here, they contribute as log 2 to the entanglement entropy, okay? By the way, for me, the entropy is minus trace of rho A log rho A, where log is the natural log, but if it's another log, it's not a problem. Okay, so the entanglement entropy in this case is just the number of singlets shared between A and B, which I denote like this, times log 2. These are very simple states, but are very important states, like if you ever have heard about random singlet phases in disordered quantum system, these are exactly the kind of state that appear. So they are simple, but they have their physical relevance. Obviously, there are much more complicated entanglement structures. You can have entanglement between 3 particles, okay? Or between 4, 5, 10, okay? All possible of multi-connection between particles. And they would contribute in different way to the bipartite entanglement entropy between A and B. But okay, that would require another course that actually a few times happened in these school courses on entanglement entropy. So you can just see the lecture online if you are interested. Okay, now that we have defined the reduced density matrix, we are ready to understand in which sense a system can attain a stationary state. So my definition of a stationary state is that we have those idea of bipartition. If for any finite, and I want to stress finite, subsystem A of an infinite system, so we took the thermodynamic limit. So under this condition, it exceeds the limit for t that goes to infinity of rho A of t, which if it exists, we call rho A infinity. Okay? Then we will say that a stationary state exists. Okay, notice now that while we formulate this definition starting from subsystem, we are making a statement of the entire system because we are saying that any subsystem does this. Okay, just that it should be finite. But if it's here, if it's here, if it's here, doesn't matter. How big it is, doesn't matter. Okay, as long as it's finite. Okay? So this statement is a statement for the entire system. And notice the order of limit, because we say that the system is finite, infinite, which means that we took the limit for t that goes to infinity after we took the limit for n that goes to infinity. This is the thermodynamic limit, okay? So this is the order of limit we have in mind. And this order of limit is very important. If you exchange these two orders, things make no sense, and you get back to the problem of the oscillation we were saying before. Okay? As long as you have a finite system, okay? For a finite system, you have quantum recurrence. That means, for example, if you look at some local observable, okay, this will make some evolution, will stabilize somewhere, but then after some time, you have your recurrence, and you have an evolution like that, okay? So the infinite time limit doesn't exist, but you stay close to a stationary state for a time, okay, if these things exist. So if V is some characteristic velocity that there is in the system, time is much smaller than the system size L. Okay, as long as you are in this regime, okay, you can observe the result in thermodynamic limit. So the mathematical statement happen only for thermodynamic limit, but if you have a finite system, like cold atom or trapped ion simulator, you have a range of times in which you can see this phenomenon. I'm just checking the time. Okay. So the next question, now we understood in which sense a stationary state can exist. The next question is, when this stationary state is thermal. As we already said, the thermal density matrix has the Gibbs form. Where Z is just the trace of, ensure that the normalization of rho is 1. And now it's very important, such thermal density matrix as non-zero the Gibbs ensemble, what is known as extensive entropy given by S thermal equal. Okay, let's call it rho T so it's clear which density matrix we have, minus trace of rho T log rho T. Okay, which is proportional to the volume because it's extensive. What we can do also from this thermal ensemble, we can define the reduced density matrix. So we can define the reduced density matrix of the thermal ensemble which we denote as rho A, comma T, equal by definition trace over B of the thermal density matrix. Okay? And now we can define the thermalization. So, definition of thermalization and I guess even the people that didn't know understood where I'm heading to. But so the definition is that if for any finite subsystem A of an infinite system, we have that rho A infinity that we defined just on the other slide is equal to rho A T. Then we say that the system thermalizes. Clear? Okay, now you see that we bypass all the big problem of before. We are not saying that rho t goes to rho t, rho of time goes to thermal density matrix, because this is absolutely impossible and make no sense. We are saying that of these two guys, that in principle are very different globally, because this corresponds to a pure state, this corresponds to a mixed state. If we look only at final subsystem, they are the same thing. There are some strange correlation in this object between very far away points that are not captured by the thermal density matrix. But okay, since we imagine to make local measurement, since everything should be local in some sense, in this, so as long as we are interested in local observable, that's what you can measure in many of the experiments, then the two states are completely equivalent. Okay? But now you can ask, what is the temperature? Is it a fitting parameter? Like the best object that we can have to match this equation? Do you expect that it's that? It's not that. Yes, Andrea? Yeah, a definition, but this definition implies that this definition should be coherent with the evolution of quantum mechanics, and if we want to define it, there is only one temperature possible. Yeah, but yeah, I gave us definition, obviously, yeah. There are the experiment that tells you that it's possible. No, but okay. The fact that the system thermalizes can be shown within the framework of eigenstate thermalization hypothesis. That is something we will discuss in the second hour. This, but as the name says, is still an hypothesis, and there is no proof. Okay, if many people have been thinking to prove eigenstate thermalization hypothesis, I invite you to think to prove eigenstate thermalization hypothesis. And but okay, still, as nowadays, this is an hypothesis, and it's okay. It's one of the most important open problem around. But okay, it could be that will remain like the chaos hypothesis in classical system, an hypothesis forever. Okay, with many evidence showing that it's correct, which we will discuss later. But now, before, let's just try to make easier stuff. What is the temperature that enters in this game? Well, it's not a number that you can play with, okay? Because in this equation that we wrote already a few times, okay, the energy is conserved. Okay, and if the energy is conserved, the energy in the initial state, okay, this is a number, an extensive number, by the way, but is equal to the energy at any time. So let's write as trace of rho t times h. Okay, and in particular, it should be equal to the energy in the stationary state. Okay, so it should be equal to the trace of the thermal density matrix times h, which, just to be clear, is trace of e to the minus h divided by t. And as you see, this is completely fixed. The Hamiltonian is the one making the evolution, so it's fixed. In this equation, there is only one unknown, that is the temperature. Okay, so you should solve this equation to find the temperature. Okay, so the temperature, says the temperature is fixed by the energy in the initial state. Which is something, again, completely obvious, because what is the temperature? It's the average energy of your system, okay? That's how you define, probably, in your basic course, and that's exactly what you find here. Yes, please. No, okay, so okay, thank you for the question. I was just skipping. This object is extensive, okay? So what we have is that psi 0, h, psi naught, divided by the volume of the system will be equal to psi, so trace of rho a t h divided by the volume of h is large enough. Okay, so let's say limit of VA that goes to infinity, limit of V that goes to infinity. Okay, obviously VA is much smaller than V, but still it's large. Okay, and this will be equal to trace of rho A infinity times H restricted to A divided by VA, and then you continue your chain of equation. Yeah, this is in fact true when this is extensive, as it should happen over in a many-body quantum system. But for example, you can already start thinking something weird if you go in a finite system too low in the spectrum. Okay, there will be not an extensive energy gap, and in that case, all this will just fail. But if you take the thermodynamic limit, you will always go to somewhere at finite energy density. Okay, but if your data are like you have a finite system with not too much energy, okay, then you are not in the thermodynamic limit. But thank you for the question. I was just a bit. Okay, and that's last thing before the break. We said what is the temperature. We can wonder what is the entropy. So the temperature is the energy in the initial state. What is the entropy? Okay, let's be more precise directly now. So the entropy, we say, is minus trace of rho t log rho t, which is proportional to the volume. Okay, we take a large, let's consider a large but finite subsystem A. Then we have that SA, the entropy of this subsystem is rho t log rho AT. okay? Which is again proportional to VA. So what we have is that the entropy density S, which is the total entropy divided by the volume, is equal to the entropy of the subsystem divided by its own volume, okay? This is almost equal in the sense that boundary terms are not there, exactly like when you show the equivalence of the ensemble in basic statistical mechanics, okay? Microcanonical, canonical are the same apart from boundary term. Here, there is exactly the same thing. These two things are the same apart from boundary term. But then, what we said is that rho AT should be equal to rho A infinity. Okay? So this is SAT. Let's say SAT. So if this is true, this will be equal to SA infinity divided by VA. Okay, this is just by our definition of stationary state, which is nothing but the limit for t that goes to infinity of minus trace of rho A t log rho A t. Okay, and this is something that just follows from our definition. Okay, there is no calculation involved, it's just definition. And what we are saying is that the entropy of your stationary ensemble, whatever it is, okay, we will see even some other things apart from Gibbs, is nothing but the entanglement, okay, which has been accumulated in time between one subsystem and the other. Okay? So the entropy of the stationary state is the entanglement accumulated in time between a large subsystem and the complement. So what happens is that just you start from a state with very low entanglement. As the time passes, correlation spread through the system becomes larger and larger, okay, until at infinite time they become extensive, and this is the entropy that is in your system. And as you see, you connect two objects that, okay, maybe in your undergraduate study were completely unrelated. Okay, entropy and entanglement actually seems two things that don't go even well together. You know always that temperature destroys entanglement. Yes, in a sense it's true, but here we are talking of a system completely isolated, so without no but to bother it. Okay, I think this is the perfect place for a break. Yes? Good. For the theory of thermalization in classical system is completely different. Okay, it's the chaos hypothesis, etc., etc. Is there, the natural question, a semi-classical limit of this object that will reproduce the classical one? I don't know. I don't think there is around, and okay, it's surely something that one should think about. No, a volume entropy. This is the entanglement entropy. What you know is that the entanglement entropy of typical state at low temperature, at zero temperature, satisfy an area law. Okay, it's well known that as soon as you turn on the temperature, area law is broken, and this is another thing. So even eigenstates that are in the middle of the spectrum, and this is actually what the ATH is telling you, the eigenstate in the middle of the spectrum satisfy a volume law. Okay? While low-lying excited state are area law. Okay, this is. Okay, if not, we make a break of 10, 15? 10? 10, good. Okay, you are all back? Okay, probably a few people were bored of the too easy lecture and did the campaign. Okay, so we understood when a system thermalizes. Now, in this second hour, I want to discuss two things. First of all, what happens in integrable system, as we have seen in the experiment of Kinoshita, Wegener, and Weiss, the famous quantum Newton cradle. And second, I want to answer Andrea's question, which is, okay, how we can prove that this actually takes the case, and I will show where the community is now, which is still not a definitive answer, but okay, closer than before. So, first question, what happened for integrable system? Okay, what is an integrable system? As you know, an integrable system has many conserved charges in the sense that exists integral of motion Im such that the commutator of this Im with the Hamiltonian is 0. Okay? Which means that they are conserved if you start from your side 0, Im side 0. This is the same at any time t. And will be the same at infinity, in the sense that we already specified before, so let me not repeat it. Okay, so this is very easy. Then you will say, okay, instead of having only the Hamiltonian in the Gibbs ensemble, you need a weight which include all these objects. And in fact, what we will say is that the system for t that goes to infinity relaxes to a generalized Gibbs ensemble, which is known as GGE, not to be confused with the place where we are in, which is GGI. You joke, but especially here, people confuse this. You can see old lecture where people just mix up the two names many times. So, and this GGE has density matrix, which is equal to e to the minus sum of lambda m Im divided by z, where z is again the trace of e to the minus sum. Okay? Obviously, needless to be said, this relaxation for t that goes to infinity is exactly the same as for thermal, in the sense that I just write the very short version. If I take the reduced density metric of a subsystem A of the GG, this should be equal to what we define as rho A infinity. Okay? So exactly as before, we take a finite system, a finite subsystem in an infinite system. We take the limit for t that goes to infinity of the reduced density matrix, and this should be equal to the reduced density matrix of the GG. Again, this corresponds to a pure state. This is the reduced density matrix of a mixed state, but as reduced density metric, they are both mixed. Okay? As before, these lambda m are not number that they could be fixed at wish. The Lagrange multiplier lambda m are fixed by the condition that trace of rho gg times Im is equal to psi naught Im psi naught. Okay, so there are many equations, one for each integral of motion, but the number of equations is equal to the number of integral of motion, and so it's a system of nonlinear equations. Sometimes it's easy, sometimes it's complicated to solve, but I don't want to solve here, I want just to say what is the theory. But things are not as easy as they appear, because you can now wonder which integral of motion I should put in my GG. Integral of motion. Should we put the naive answer is all, correct? Everyone is conserved, everyone constrained the dynamics, everyone satisfied this equation, so why not? Okay, if I'm asking, there is a why not. Okay, the point is that a generic quantum system, an arbitrary, let's say, arbitrary, quantum system has too many integral of motion in the sense of conserved quantity. Let's just build an example. Imagine you have an Hamiltonian, H. You can write the Hamiltonian as sum over the energy level okay? This is just the definition of the Hamiltonian, the projector on the eigenstate times the value. Okay? And imagine now that you have a spin, just to be clear, a spin system. You have n spin 1/2. Okay? How many energy state? Q to the n, no? Exactly like as many element of the Hilbert space. But you see what is the problem now? That this projector, so if I define OM equal the projector on an energy eigenstate, this OM commute with the Hamiltonian by definition, commute with itself and is orthogonal to all the other. So all these Q to the n object are linear independent and conserved. So we have a problem here. Usually you say that if you have n degrees of freedom, a system is integrable if you have how many integral of motion? N. You have Q to the n. So we just proved, without making any calculation, that all quantum systems are super integrable. They have Q to the n integral of motion. This is obviously not true, okay? Okay? Because else, by the way, if this would be true, no system will ever thermalize, and okay, so all the course will be completely useless. The solution of the paradox stays in the locality of the integral of motion. So, in my language, then you will learn, because in the literature, two things are referred as local integral of motion, okay, integrability community. A local integral of motion is an object that can be written as the integral over the space of some energy density corresponding to the integral. Okay, or if it's a lattice model, replace the integral by the sum. Okay, exactly like, for example, the Hamiltonian is the integral in the x of some energy density, okay, which, if you like, CFT is nothing but T00x, just for the, or in a lattice model, H is the sum over J of usually some next neighbor object A, J plus 1. Okay, this is what you write on the lattice. These objects are local. Okay, can be local on 2, 3, 4 sides, but not infinite. Okay, so these are local integral of motion. Okay, and I'm telling you that in the GGE, one should put only the local integral of motion, actually a bit more that I will discuss in a second. What is the idea why this is the case? Because since we are defining the thermalization, the relaxation to a GG, in this case, at level of a subsystem. Now you see that if an integral of motion is local, okay, if I can restrict this integral to A, and I get an extensive value, I enlarge this A, I get always the same density times the volume, okay? So this is extensive. If instead I take these strange guys, these are objects that are localized everywhere, and if I calculate it in a subsystem, you can just get 0. Okay, these are spread all over the system. I take a subsystem which is finite in an infinite system, and the overlap in a finite subsystem will be just something order 1 over L. Actually, will be volume A divided by V. So let's say that trace of rho A, this projector, I will naively expect to scale like the volume of A divided by V. And if I take before the volume V that goes to infinity, this object just goes to 0. So for this reason, these kinds of objects should not matter in the way we define thermalization. If we would have defined thermalization in another way, another strange way, then we would have find problems. Because we would take into account correlation for very far distant points that in fact are encoded in this projector. Okay? So this is we are talking about integral model, and we can make many calculations. Is this true? Now, this can be proved, but before there is a small thing. Okay, that what happened? Okay, so this idea were around like 10 years ago, more or less. In 2015, there were 2 independent calculations by the Budapest group and by the Amsterdam group, showing in 2 different cases that actually the constructed stationary state, because in the stationary state that you can do you can construct explicitly in integrable model, did not coincide with the generalized Gibbs ensemble built with all known integral of local integral of motion. What you will conclude out of this, don't conclude that this ensemble is wrong, or it's failed. That was the hope of many people at the time, but this is not the case. What was happening is that, okay, if it's not, in Italy we say if it's not super bambagnato, what was happening, can you try to guess? Why I stressed known integral of motion? Okay, because there were some unknown integral of motion that were not taken in the game. And these unknown integral of motion are quasi-local, okay? So there were unknown quasi-local and by quasi-local I mean that the integral, so this IM quasi-local, instead of being the integral over only one thing, is the integral over 2 points with the kernel x minus x prime times some IM with this kernel that decay fast enough to guarantee that this object is extensive, okay? Okay, so remember what I just said before, that we have to put this integral motion because they are extensive. Are they the only extensive integral motion? No, there are also these quasi-local ones that were, some were known, but the ones that were known had expectation value 0 for what they have done. So they were unknown and they were discovered thanks to this thing. Okay, and then in 2016, a bunch of other people, started the group of Amsterdam plus Thomas Prosen and Fabian Hessler, proved what is nowadays is known as string charge duality, okay, which basically prove what I'm telling here. This is proved nowadays. There is no, it's not a conjecture. For an integral of motion, starting from quite generic initial state, okay, with some condition that I'm not going to say here, they're too complicated. The stationary state is the generalized Gibbs ensemble built with all local and quasi-local integral of motion of the theory. Okay, and this thing, for some reason, technical reason that the expert of integrability in the field here knows, is known as string charge duality. Okay, charge because are the charge integral of motion, and strings because are the state in this integral mode. In this integral model, satisfy the so-called string hypothesis. Okay? And this will finish the first part of this second hour. I have still 15 minutes to tell you about ATH. Questions? Yes. Well, you can say, yes, if you have only the energy is conserved, you have Gibbs. Like, if not even the energy is conserved, you have the identity, which happen. Okay, this quantum circuit don't conserve anything. Okay, then you can say if you have energy and particle number, okay, then I have like a grand canonical ensemble with 2 integral of motion. I can build something with the 3rd integral of motion, yes. Then I should put 3 integral of motion. These are very, we can call them generalized Gibbs ensemble, but are just variation of the Gibbs ensemble, nothing special. But you can imagine to add 1 by 1 until you arrive to have infinite of them, and okay, there is a full family of GG depending on how many integral of motion your system has. So the things go smoothly between one extreme and the other. Just that the 2 extreme are the easy one, and in the constructing model with, okay, with a conserved particle number is easy, but already with 3-integral of motion, it's not so trivial. Okay, you should think a bit to find that one, and then if you want a model with 7 integral of motion, good luck, I don't know, but probably you can do. No, it's not sharp. It's you go smoothly from one to another. I show you the two extreme, but. This. Yeah. It's if you everything is well defined in the thermodynamic limit. In a finite system, obviously you are on a lattice. The first integral of motion is the particle number C dagger M C M. The energy then is C dagger M C M plus 1 plus Hermitian conjugate or other things like that. The third integral of motion will have Cm plus 1, Cm plus 2, with 3 objects at distance 2, and so on and so forth. Obviously, if you are in thermodynamic limit, these objects are all very small. But if you are in a finite system, you should take care in how you take the limit. In fact, there were very nice papers by Hessler and Fagotti where they were showing how you can reach how many integral of motion you should put if you are interested into a subsystem of dimension 10, okay? Yes? A function, so if it's a linear function, it's not independent, it's nothing. If it's a nonlinear function, it will be non-local, so you should not include. That's like h, you make h square. H square have terms that to every possible distance, okay? More question on this? Okay, if not, let's use the last moment to discuss ATH, which will be something that Dima will try to break all time. ATH means eigenstate thermalization hypothesis, okay? So we go back to our initial state that we write at sum over some overlaps on the energy level, okay? These are sum over the Hilbert space, okay? You can always write it. The energy eigenstates are a basis, and you can write always something like that. And this is exactly what you find also in von Neumann paper, by the way. The time-dependent state in this basis is simply sum over alpha, C alpha, e to the minus E H alpha T, H alpha. And you see that the state itself will oscillate, okay? Not that will asymptotize. But now, let's consider a local observable. Let's call it A, one of those objects that we want to thermalize. So at time t, the expectation value of a local observable is psi t A psi t, which if I expand in this basis, is just sum over alpha beta, C alpha star C beta, e to the I minus H beta minus H alpha, A alpha beta, where I define H alpha beta, the expectation value. E alpha, A, E beta, okay? It's few body quantum mechanics. There is no thermodynamic limit yet, okay? And for t that goes to infinity, assuming that this limit exists, okay, so if the limit exists, I can say that the limit is equal, t was here, sorry, the limit is equal to the time average if it exists, and so this just gives you a delta function here, alpha beta, and you get sum over alpha, C alpha absolute value square, A alpha alpha. Okay, so if the limit exists, that's what we want to show. That is the limit. But we want this to be equal to the thermal expectation. And in particular, now we go to the microcanonical average. Okay, so keep in mind this formula. Now, what is the expectation value? Is the expectation value of A in the macrocanonical ensemble? A on the microcanonical ensemble. I remind you, okay, first of all, rho microcanonical is just the sum over the energy level which E alpha that belonging to H minus some delta, H plus some delta of E alpha, where we normalize 1 over n, where n are the number of states that satisfy this equation. Okay? So this is the microcanonical ensemble as you define in standard statistical mechanics course. The expectation value of A in the microcanonical ensemble then is just 1 over n, sum over alpha, A alpha alpha. Alpha obviously always in this sum over E alpha in this window here. Now, if the system thermalizes, you want this to be equal to this. And this seems quite difficult. Okay, here there is all the information on the initial state. There are all these C alpha that depends on the initial state. Here, obviously, it's microcanonical ensemble, there is no initial state. Okay, how these two things can be equal? It sounds crazy, but the answer is in the eigenstate thermalization hypothesis. I write in Word before writing in formula. The ATH states that 1, the diagonal element A alpha alpha vary very slowly or smoothly as function only of the energy. With difference between close values that goes to 0, that goes exponentially to 0, as L that goes to infinity. And the second statement of ATH, which we will not use here, but that it's important for other stuff, is that 2 of diagonal element are much smaller exponentially actually, but we don't have, then and random. So in formula, A alpha beta, read like the average value delta alpha alpha where A alpha is just a function of E alpha and of nothing else, plus some number that I don't want to write, a random function, like a random, exactly the one that Greg was teaching you, okay? And then the fact that this is small is because it's a function of the entropy. Okay? You see that if you have this assumption, now you have this A infinity that is here. It's sum over alpha, C alpha square, A alpha alpha. Okay, but this is a smooth function of the energy, so it's almost constant. You can bring out. This is A bar, and then you have sum over alpha of C alpha square, which sum to 1, and you have H bar. And in the same way, the microcanonical H is, well, where it's written, there is 1 over n, sum over alpha of A alpha alpha. And okay, so here you get always the same value, A bar, divided by n, sum over 1 in this shell, which gives exactly n, and this is again A bar. Okay? So, but what is, let's see the physics. Imagine that you want to plot the expectation value of this observable A alpha alpha on an energy state as function of the energy. What this state normalization hypothesis is that there is a smooth limit, and okay, let's say we are at some L1, for example, equal 10, 20, whatever you want. These points will be spread around this curve, okay? There are many points with a given width. Okay, then if you make the same plot for L2 much larger than L1, you have the same master curve, but now the spreading is smaller. And as you go to thermodynamic limit, this becomes just a curve. Okay? And now you see that you have two possibilities to break against the thermalization hypothesis. That will be DIMA work. Or, first possibility, this object doesn't reduce when you take thermodynamic limit. This is what happened also in integrable system, okay, because there are one curve for each integral of motion, and what happened in many body localization. Okay, you increase system size and this stays a chunk. And the second possibility is to have outliers. You have all states that satisfy ATH, but then there are some outliers here that they stay there, they remain there. Okay, these outliers are called many-body scars, quantum many-body scars, and it's another thing that Dima will discuss. Okay, so the basic idea is, if this band will become smaller and smaller, you are guaranteed to get the microcanonical ensemble. By the way, this is to be proved. No one knows how to prove it, okay? But then one can make this plot numeric. It's plenty of numerics like this one, like if you search Marcos Rigol, or even recently Fabian Esler made some very nice generalization of ATH for integrable system, how it generalized, and there are some, you can make similar plots for resolving the various integral motion also for integrable models, okay? And okay, and there are many other people that I don't, I cannot mention all of them here. And by the way, these outliers that are scarce, not if you have one outlier, it will have 0 weight, okay? You have a band of outliers, so some class of state. Usually what happens is that while here you have q to the n state, in this outlier, in this quantum many-body scarce, you have only n states. But even if it's only n, so in a sense ATH is still valid, you can naturally find some initial state that couple only to those states. Okay, like some super selection rules there are in the game. And so there are many very natural initial states, not artificial ones, that don't have any overlap here, but overlap only there. And for this reason, then this state will not thermalize. Okay? And this finished my introduction. Okay? And Dima will finish up. Questions? Up or down? But because, you know, this C alpha, since we expect the system to, the idea is that this C alpha are peaked close to the average, to the mean energy, and they decay very far away from that. Okay, so this is, which must be because of conservation of energy, okay? As the system times goes to infinity, again. Okay, so if you plot C alpha as function of V alpha, okay, which goes together with the hypothesis if you want, this you always expect that if you are at some L, these are this, I write just the distribution, I don't write the point. At some L, they are distributed like this. If I take a larger L, they will be distributed like this, and for larger and larger, it shrinks. As it should be by conservation of energy, okay? So this is, one can make this very robust. It's not, let's say it's not part of the hypothesis. Alberto? Here they don't enter. They enter in many other things. If you are interested, see the paper by Pappalardi, Foini, and Kurchan, where they make the connection with these things with free probabilities. That is very nice. And okay, it's exactly these guys that are related to free probabilities. But okay, I had 2 hours for introduction. That's yeah, okay. We believe statistical mechanics, at least that, and they should be equivalent. Okay, then here it's more natural to introduce the microcanonical because the energy is conserved, so you are. The temperature is, it exists for a microcanonical system, obviously, it's the energy, but. Yeah, they're physical. It's plenty of, no, okay. So, this to be said, usually, to make a proper connection, I say that the operators, for example, are local, but usually when you find in the literature of ATH, what people say, there are a set of operators, whatever they are, we don't care, that satisfy these properties, and this will be the one that thermalizes. Okay, I'm saying that if I want to understand thermalization in that way, this should be valid for all local operators. Then if there are other operators, I don't care. If not all local operators satisfy, it's a problem. Okay, and so the same thing for the state. There are a given set of states that have this property, and if this doesn't happen, it means that the state is non-physical and will not thermalize. Okay, you already conclude that if this is, if this stays large, it doesn't thermalize. So. Not that I'm aware of, okay? Okay, if not, we can go for lunch. Thank you for your time.